All right. Let's, if you guys would please stop talking. We'll take some questions from the homework to start. Does anybody have questions from 1 through 22 that they'd like to talk about? Ella. Number 7? Sure. So the first thing we'll do, it's asking for the magnitude and direction. So to calculate the magnitude, I'm just going to use the component form formula. 3 squared is 9, negative 4 squared is 16, 9 plus 16 is 25, the square root of 25 is 5. And then to get the direction, what I'm going to do is I'm going to plot this. So 3, negative 4 is down here. Actually, let me draw that vector in a different color. So the direction we're looking for is this one. So I'm going to do 360 minus alpha, where alpha is that angle there. So the side lengths of this triangle were 3 and 4, so alpha is going to be tan inverse of opposite over adjacent. And when I type that into my calculator, the tan inverse of 3/4 is about 36.87. So 360 minus that is 323.13. Does that make sense there? Oh no. Well, I will make a note and take a look at that. Okay.
I got the same answer on the key.
So I will take a look at it and think about it a little bit more, but oh, okay. How many of you wrote the angle as negative something or another? No.
I had that, but I was like, wait, I want to get the answer.
So I'll take a look at that and see what's going on.
My inverse tangent of 4 over 3 comes out to 53.1.
Oh! I wrote down 3/4 in my calculator. That would do it, huh? Yeah, see? That would do it. There we go. Easy fix. Thank you guys for not letting it go and figuring out what it was that I did wrong. So that was good. Thank you. Ben. Ella, you happy now?
Yes.
Okay. 18 it is. So it says it wants the magnitude and direction, or the component form and magnitude, excuse me. So the first thing I'm going to do is I'm going to turn CB into a vector and component form. So it's going to be the terminal minus the initial, and then we'll have the terminal minus the initial. So that gives me 7, negative 13 for CB. And when I do the same thing for BD, so the terminal minus the initial, and then terminal minus the initial. So far, so good. Okay. And then I'm going to just plug in these. So that's going to give me negative 35, comma 65 plus negative 6 root 2, and then 10 root 2. So when I add those together, I'm going to have negative 35 minus 6 root 2, 65 plus 10 root 2. So there's my component form. And then to find the magnitude, since it doesn't tell me I need the exact form for the magnitude here, I'm going to use my calculator to do this because it'll just make my life a little bit easier. So I'll do negative 35 minus 6 root 2. Oops, I said 2 squared plus 65 plus 10 root 2 squared. So that should give me about 90.30. If you wanted the exact value, that's going to be a little bit of a slippery guy to get, because you're going to have square roots under square roots, which is kind of gross looking, but you do what we wrote down in the calculator. You just have to do it by hand, which is awfully annoying. I have a feeling the answer key listed the decimal. Did it not? Oh, is this an even one?
Yeah.
Okay. Yeah, so they probably gave decimals for this problem though, right? Yes, we were giving decimals for these also. When we did give answers, we gave both the exact and the decimal. Here I wouldn't even bother with the exact because you have roots under roots, and that's stupid. Are you okay with that, Ben?
Nope.
Okay. Anyone else from this assignment? Ella. The answer for number 12 is 0.73, comma 2.73. Sid? 22? So it says find the unit vector in the same direction as the vector listed. Write your answers in component form as well as linear combination form. Okay. So I know that my unit vector is going to be 1 over the magnitude of vector v times vector b. Hi, Brockton. Thanks. So far, so good, Sid? Okay. So we'll start by calculating the magnitude for b. So 36 plus 121 is 157, and that is not a perfect square, so I'm not going to bother with it beyond that. So stop talking, please. I have 1 over the square root of 57 times 6 negative 11. So that's going to be 6 over the square root of 157, comma negative 11 over the square root of 157. And then we rationalize that denominator. So that's 6 root 157 over 157. And negative 11 root 157 over 157. And I don't think either one of those reduce. Let's check real quick. So 6 over 157. Nope. And 11 over 157. Nope. So that's my component form. To write this in the linear combination form, all I do is I take the x component times vector I plus the y component times vector j, because remember vector I is just the vector 1, 0, and vector j is just the vector 0, 1. So this will, if you compute this all back out, it would still give you those, their equivalent. Is that okay there, Sid? Yeah, of course. What's up, Ella? You're making some faces. Oh, okay. You keep on reading. No rush. Overall, how'd this homework go for you guys? Should have been pretty easy, right? The computation isn't terribly difficult on these, right? Most of the problems are reasonably quick. It's not super tedious. The thing you have to kind of get through is you have to get through the notation and the vocabulary to make sure you understand what we're asking for in the problems. But the problems themselves are rather straightforward, right? They're just little computations. Okay. Any final questions from the homework? Great. So we're going to pick up where we left off in 8.2, talking about operations on vectors. So the last thing we had talked about was these unit vectors and a way to get a unit vector in the same direction as some other vector, and then how we can use these special unit vectors I and j to write our vectors in this linear combination form, right? What we're going to do what we're going to start with today is we're going to define another vector operation called the dot product. So if u is the vector u1, u2, and v is the vector v1, v2, we say the dot product of v and u which we denote as u dot v is found by u1 times v1 plus u2 times v2. Probably get rid of that. So right away, something should stand out that's decidedly different about this vector operation than all the previous vector operations we've seen. What kind of result are we getting? When I take the dot product of two vectors, what kind of quantity am I getting as my result? What kind of number is u1 times v1 plus u2 times v2? This result is a scalar, right? That's just a plain old regular number, not a vector. So this is the first operation that we've seen that takes vectors and turns them into a real number. Everybody's okay with that idea? Last year in your algebra course, do you remember that if there was when we talked about matrices, most of the time when we do an operation on two matrices, we get another matrix back, right? There was one operation, though, that gave us a real number back. Do you remember what that was? It was the determinant, Remember, the determinant of a matrix is a real number, not a matrix, right? Similar thing going on here. The dot product of these two vectors is a real number, not a vector. So let's look at some properties of dot products. So the first thing is the dot product is commutative. That means that u dot v is equal to v dot u. There's a multiplicative identity property. So if I take the dot product of any vector with 0, what do I get back? Get 0. Notice not the 0 vector I'm getting back. I'm getting back the number 0. There's a distributive property. Oops. So if I do u dot the quantity v plus w, that dot product just distributes across the sum. And because the dot product is commutative, it doesn't matter whether we which side the dot product is on, whether it's on the left or the right. There's a scalar associative property, which says if I have k times u dot v, that's the same thing as u times k, or u dot k times v, which is also the same thing as k times u dot v. So what this is basically saying is it doesn't matter when you multiply that scalar in. If you have a scalar times a bunch of things dot product together, you can multiply that scalar in at any point. You could do it to the first vector, the second vector, whatever vector, or you could just wait and do it all at the end. It doesn't matter. And the last one is the magnitude property that just says a vector dot itself is the same as its magnitude squared. So in the homework, you're going to be asked to prove these. Let's do one of them right now. Your guys' pick. Which one do you want to prove? Okay. So I'm going to start by defining the component form for my vectors. So I want to show this, right? Everybody okay with that? So basically what I'm going to do is I'm going to figure out, yes, Brockton. WTS is want to show. Yep. So what I'm going to do is I'm going to just figure out the component form for each one of these three versions. And if they have the same component form, then they have to be equal, right? So I'm just going to start by plugging in the components, right? Then I'm going to do the scalar multiplication. So k times u1, u2 is just ku1, ku2. That's just the definition of scalar multiplication, right? Then I'm going to perform my dot product. So that's going to be the x components multiplied together plus the y components multiplied together. And since k, u1, v1 are all real numbers, I can just write it like that, and I don't need the parentheses, similar with k, u2, and v2. So now I'm going to take the middle part of what I wanted to show, and I'm going to do the same thing. So, just like before, you'll do the scalar multiplication. And then we'll perform the dot product. Give me this. And because u1, k, and v1 are all real numbers, I know I can multiply them in any order I want, so I can write them in that order. Similar, u2, k, and v2 are all real numbers, so I can write that multiplication in any order I want, so I'll write it in that order. And I have that the first two things are equal, right? Because they have the same components. Everybody okay there? Okay. And then the last piece was k times u dot v. So that's k times u1, u2 dot v1, v2 So per definition of the dot product, I'll do that. And then I just distribute the k through. And that's the same thing. So all three of those gave me the same result. So they must all three be equal. Does that feel okay there? So you can omit this one when you're doing the homework, or if you wanted to, for completion's sake, you can copy in the result here that we proved in the notes, but we did this one here together. You would do the other four a similar fashion, where you're just going to define the vectors into component form and use those component forms to push through the formulas and show you get the same thing. Ben? Maybe. I haven't written the test yet. Okay. So just a quick computation. Let's say that U is the vector 2, -3. V is the vector -1, 5. And W is the vector 8i plus 4j. And suppose we want to evaluate U minus W dot 2V. So first thing that I would worry about is getting the vector W out of this linear combination form and into component form. So what's the component form going to be for vector W? 8, 4. Very good. So the I is the X and the J is the Y. That's it. So when I fill this in, I have U minus W dot 2V. Okay. So order of operations says the first thing I should do is the subtraction. That gives me 6, -7. 2 minus 8 is -6. -3 minus 4 is -7. And then I'll do the scalar multiplication. So that gives me, 210. 2 times -1 is -2. 2 times 5 is 10. And now I'll perform the dot product. So I multiply the x components together, multiply the y components together, and then add them up. So I get -58. Everybody feel okay there? So the dot product's not a difficult computation to make, right? You just multiply the components together and then add them up. Now this dot product is going to be a rather useful calculation because we can do a couple of different things. So let's say we want to calculate the angle between two vectors. So let's say we have something that looks like this. Here's my vector U and here's my vector V. What we're looking for is this angle here between the two of them. Now we could calculate this using right triangle trigonometry, but it's kind of tedious. We have an alternate way of doing this by using the dot products. So, why is this true? Why is that true? Should we prove this? Probably shouldn't take me at my word, right? We can prove this just by using the law of cosines. It's not too bad. So I'm going to draw in this vector to make a triangle. What is the name for this vector going to be? This is vector v minus u. How do I know that? How would I know that that's u minus v?
Because u is below the x-axis. I have no idea.
So if I look, this vector and this vector are put head to tail, right? Can you see that? So if they're put head to tail, that's the same thing as vector addition. So that's telling me u plus v minus u should equal v, which is exactly what I'm saying, right? So here's my proof. By using the law of cosines, I can say the magnitude of v minus u squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times cosine theta. Is everybody okay with why that's true? You remember the magnitude property from just a moment ago? So it says the magnitude squared is equal to the dot product of the vector with itself. So I'm going to use that here to do that. Everybody good there? If I have the distributive property, what is that going to allow me to do there on the left-hand side? Means that I can FOIL. Now look at these two pieces. What do you see here? I see the magnitude property, right? These two are like terms, so they can go together. If I subtract v, or magnitude of v squared from both sides, yes, sir?
If there's two v's being multiplied, would it be times 2v? Or times v squared?
So what I'm doing is I'm using the magnitude property here.
Right. There was like in between the two that are highlighted, where you made it negative 2u times v, why is that v equal to 1? It's like, it's u times v and then u times v again.
Mm-hmm.
Two v's.
No, there's two u times v's.
Oh.
And if I subtract magnitude of u squared from both sides, those cancel. Everybody okay there? Now what I'm going to do is I'm going to divide both sides by negative 2 magnitude of u times magnitude of v to get the cosine by itself. So the negative 2's can cancel. And if I take the cosine inverse then of both sides, I am done. So this formula here to calculate the angle between two vectors is really just an application of the law of cosines. Bella?
Do we ever use like numbers for this? Or is it just
I was proving the formula. Is what I was doing. So in a proof, no, we don't ever use numbers.
So are we gonna have to like do this kind of proving like on our own?
Well, there's some proofs in your homework. Okay, so let's say we want to find the measure of the angle between these vectors u and v. So if we're looking for the measure of the angle between two vectors, we're going to be using this formula that we just proved a moment ago. So for this formula, I need three things, right? I need the dot product of u and v. I need the magnitude of u and the magnitude of v. So u dot v is 2. It's 85. That's 8. Okay. And now I'm just going to go to my calculator. So cosine inverse of the fraction 2 over, stop talking please, square root of 85 times the square root of 8. Oops. That gives me 85.6. Everybody okay there? Everybody feel okay with that example? Again, nothing too terribly complicated going on there, right? Just have to follow some formulas. So we say that two vectors are orthogonal if and only if their dot product is 0. When we say orthogonal, what we mean is that they are meeting at a 90-degree angle. So suppose I was asked to show that two vectors are orthogonal. We can do that just by computing their dot product. So -5 times 16 is -80. 8 times 10 is +80. -80 plus +80 is 0. Let's use, oh, interesting. I thought there was all going to be one thing. I don't want to do that then. That closes section 2. Stop talking, please. Unfortunately, with the schedule kind of the way it is, I can't go and waste like 15 or 20 minutes in the middle of a chapter. It's fine every once in a while to do that, but there's going to be places where we're really going to have to pause and need a chance to practice things much later on that I want to make sure that I've budgeted the time for. While I understand that you don't want to do anything more today, we kind of need to keep on moving because we haven't yet really gotten to the difficult parts, which I do want to be able to slow down and take time for. No. Okay. So I want to talk here about these bearing problems. we did these first semester, and what we did first semester was basically vector story problem, or these problems, we did them as vectors. We just didn't have all the formal language to do this. But let's rerun through an example of how we did this. Okay. So a boat leaves a port and averages 40 knots for 2 hours on a course of 215 degrees. Then it turns to a bearing of 162 degrees at 55 knots for 3 hours. What is the distance in bearing relative to the port? So what I want to do is I want to start by sketching a little picture of what's going on. So the first part of the trip, the boat is going on a course of 215 degrees. Remember when we're talking about navigation, where does our angle begin? The north. And which way does it rotate? Clockwise. So starting at north, 90, 180, and then like 35 more makes 215 degrees, right? But I don't want that angle. I want this angle. What is that angle going to be? It's going to be 180 degrees plus that 55-degree angle. Okay. So if I refer to this as vector v, the magnitude of vector v is going to be the length of that vector. We're going 40 nautical miles per hour for 2 hours. That should be 80 nautical miles. So the component form then for vector v is going to be 80 times cosine of 235, comma 80 sine 235. So my second leg, I turn at a bearing of 162 degrees. So 90, and then like 72 more puts us down there. And again, we don't want that angle. We want this angle. which is going to just be 360 minus that 72. And if I called this vector u, the magnitude of u is going to be 3 hours at 55 nautical miles per hour, so 165 nautical miles. Bless you. So vector u is going to be 165 times cosine of 288 times 165 sine of 288. Where did I get what? Yes. Because that's the angle that I'm looking for. I mean, you could have done 270 plus 90 minus 72 if you wanted to do that. That's fine. I'm just trying to find the size of that blue angle. Each quadrant is 90 degrees. So you can add up from a total or subtract from more than. Either is fine. So what this boat trip looks like then is we do this. That's my vector v. Then I do something like this. That's my vector u. And what I'm looking for then is this vector v plus u. Everybody kind of agree with that? What? No. Because it's literally vector u. So then v plus u is just going to be 80 cosine 235 plus 165 cosine of 288. And then, oops, we got the 0 there. 80 sine 235 plus 165 sine 288. When I type that into my calculator, I get 5.10 negative 22246. So if I want the magnitude of that, I do this, and I get about 22251 nautical miles. And then if I draw my picture, if I plot the point 5, negative 2222, it's like down here somewhere. So the direction that I'm looking for is this angle here. So this angle, theta, here, is going to equal 360 minus alpha, where alpha is that angle there. So the side lengths here are 510 and 22246. So alpha is opposite, or tan inverse of opposite over adjacent, which comes out to be 88.69. So when I subtract 360 or 8869 from 360, I get 271.31 degrees. So there's my magnitude and direction. What angle? That's this work here. So I plotted the point, and I found that angle alpha, and then I did 360 minus alpha. Now, actually, I don't think I wanted this as a direction. I wanted a bearing, right? So this isn't quite the answer that I wanted here. My apologies. I just got going and I forgot the question. Because what we're looking for is a bearing, so we want this angle. Which is fine. That's just going to be 90 plus alpha. So 178.69. My apologies. So for next time, you guys should do 23 through 40.